The regular Falsi method is actually a very old method for finding the solution to an equation in one unknown, and it's similar to the bisection method, but it does take a different approach. So let's take a look at how it works. Once again, we're solving the equation f of x equals 0, and we have knowledge of the solution being on some interval from a to b. So let's once again do a drawing and see what we get. Alright, so let's have the y-axis here, and let's have the x-axis going like this, and let's assume that the line that we're interested in, the function, goes something like this. Okay, so if we find 2 points which are sufficiently bracketing the interval, let's say we'll have a here and b here, we can once again calculate f of a, which is going to be around here, f of a, and then f of b at this point, f of b. And in the bisection method, we basically split the distance between a and b halfway, and we went with that. But with the regular Falsi method, we're going to do something different, because instead of doing this, what we're going to do is we're going to draw a line which connects the point a f of a and b f of b, and we're going to draw a line. So I'm going to draw a line like this, and instead of taking the halfway point between a and b, we essentially look at the intersection of this particular line with the x-axis. So remember, we're looking for this point. We're looking for this point, and we're attempting to get closer to it by first of all considering this point, because this is the first point of intersection. So let's call this point C. So once again, we grab this point, we calculate f of c, and then we apply Bolzano's theorem once again. So just like in the previous example, what we're essentially doing is we're looking at whether the sign changes between f of a and f of c, or whether the sign changes between f of c and f of b. And we continue doing this. So for example, we know that the solution is between c and b. Therefore, we once again draw a line between this point and this point. And you'll see that as I draw this line, it gets us closer to the solution. So we get a new point D, and we can once again draw a line, and eventually we'll get to the right solution. So if we were to actually formalize this whole thing in terms of mathematical notation, then we can say that the following. So given the interval from a to b, the equation of a straight line that actually connects the points, let's say point b to f of b, to the point a f of a, is given by the following. So we have y being equal to f of b minus f of a divided by b minus a times x minus b plus f of b. So this equation here is the equation of the line from this point to this point. And then, of course, as we've seen before, we actually apply Bolzano's theorem, meaning that if f of a, f of c is less than 0, this means that the solution is between a and c, and if f of a, f of c is greater than 0, then the solution is between c and b. So there is to it. Now let's take a look at how it's done in MATLAB. Okay, so here's an outline of how we would do this in MATLAB. Once again, we have a function, and it's a similar function to what we had for the bisection method. And then we have the assumption of the range going from 2 to 3, and we have the maximum number of iterations. We once again have the tolerance, and this time around what we're doing is for each of the iteration steps, first of all, we apply this calculation. That's the calculation that we had in the in the previous demo. So that would be this part. We calculate the y using this particular formula, and then what happens is we look at whether we're hitting the tolerance marker that we are actually interested in, meaning that we are getting the kind of tolerances that we want, and then we simply adjust either a or b depending on the sign of f of a times f of c. So that's pretty much what all that it does. And as we run this, you'll see that in just 4 iterations we're getting to within the kind of distance that we're happy with.